irrotational, then clearly H is a constant in the entire flow region. The steady flow means there is no variation in time. So the gradient of H is 0, which all the spatial derivatives of H are 0, which means H remains a constant throughout the flow. This is something that's valid for, because the flow is irrotational throughout the flow region. So the H will also be a constant over the entire region. So we know the quantity H at one point, then the quantity H will be the same. This is probably the strongest form of the Bernoulli theorem. H is a constant throughout the flow region. So the conditions here various other conditions we discussed the potentially body would be expressed as the gradient of a potential, and then we saw that the pressure is really a function of only the density. Either the temperature is a constant or the temperature doesn't influence the pressure to a large extent, so that constant, and then we inverted the density and expressed in the pressure here. So this is what it is for a perfect fluid undergoing steady irrotational flow. So the underlying all of this, then H is a constant in the entire flow region. If we relax the condition and say that the flow is not necessarily irrotational, then we are left dealing with this. Right? So this is what I pointed out. Now to explain this, what this means. Now, what can H be a constant across? Right? So, suppose let's say I consider a surface given by H of, let's say, x1, x2, x3 equal to a constant. Just considering a surface. Forget about this equation. So now, for this surface, if I take any point, we have seen that the normal, right, would be the outward normal, but anyway we have to only the direction. So the direction of the outward normal, let's say I take a particular point, would be given by the gradient of H, right? This is dH by dx1, dH by dx2 and so on. That would be the vector along which the normal to the surface would lie. Right? Now we are given that this is the normal to the surface. Normal to H equal to C surface. So what we are given is that the gradient of H at any point is given by P cross W, right? So the normal is also parallel to P cross W. So the P cross W, if I calculate that vector, it would also have a direction because along the normal to the surface, right? So then, if you now look at the cross product of two vectors, we have seen that the direction of the cross product of two vectors is in a direction which is normal to the plane formed by the two vectors, right? So the plane formed by the two vectors here, B and W, can be written as alpha times B plus beta times W. That will be the plane, that will contain all the vectors in the plane formed by B and W. Alpha equal to 1 and beta equal to 0, we get B. And if alpha equal to 0 and beta equal to 1, we get W. Those are only two vectors. There is an infinite number of vectors on that plane which are given by this. So clearly, so this is parallel, and then this is so we can clearly see now that since the this is perpendicular actually, because of this perpendicular to the plane of formed by B and W, which is represented by this. Right? So that certainly would imply effectively that the plane formed by B plus W would be a tangent plane. This plane is tangent to the H equal to constant surface. This is actually how the normal is effectively defined, and you can actually get the formula that the normal is given by the gradient by first finding the equation for the tangent plane to a surface, and then say that the normal has to be perpendicular to the plane. Right? So we've sort of gone the reverse way. Right? So what does it mean? So any vector on the tangent plane, the meaning of something being normal to the plane itself means that if you take any vector on the plane, right, then the normal would be orthogonal to that. Right? That's the meaning of the normal to the plane means it is normal to or it is orthogonal to all vectors in the plane. Right? So that would clearly mean that V dotted with, because we know that alpha V plus beta W any vector in the plane, the dot product of that with this is 0. Clearly then, this applies to all values of alpha and beta, clearly then V dotted with is 0 and W dotted with is also 0. What we wanted to prove was to ask the question whether the quantity H is it constant along a streamline or a vortex line, what is implied by the statement in Aris. So I can now keep this aside and move entirely to address that question. Is H constant? The quantity H along a streamline. Now let me now consider the equation of a streamline. We can see that a streamline is a curve in space and it can be represented by a single parameter in the following way. So let this now be the streamline. Of a steady flow, H itself is a function only of a steady flow. It is a function of the position in general. Right? So now we want to evaluate H along a streamline. Right? So I choose a particular streamline and I want to evaluate H. Right? So H along a streamline. Along the streamline would be given by H of each point on the streamline. I can calculate H like this. So what this means is that now H is expressed as a function of tau along the stream. Right? So now to prove or to answer the question whether H is a constant along a streamline, which quantity you would calculate or evaluate now? To prove that something is a constant, what should be 0? Its derivative of H with respect to now what? With respect to tau. Right? So I can ask the question, is dH by d tau, is it equal to 0? dH by d tau is given by the chain rule as dH by dx1 times dx1 by d tau. And in fact I can write using the summation, repeated index summation convention as dH by dxi times dxi dotted with d tau. Why is this 0 or is this 0? Why is this C based on whatever we have written here? Which equation here matches with that, this quantity? What is this equal to? It's clearly equal to the gradient of H dotted with B, because B is nothing for a streamline dxi, which is given by this parameter representation. The definition of the streamline is that V1 is dx1 by d tau, V2 is dx2 by d tau, and V3 is dx3 by d tau. Clearly they prove that H has to be constant along a streamline because of the fact that V cross W is a state that is being used. So we use it here. This leads to this picture that I conclude this, clearly this leads and answers the question that when we have steady flow of a perfect fluid is not necessarily irrotational, then H will be constant along a streamline. Now, I can simply answer the question whether it's along a vortex line, and I see that then the vortex can be given by a parameter something like this, right? So this is now equal to W, so that would also be 0. So the same rule applies for the vortex line also. So this proves the fact that if considering steady flow of a perfect fluid, it is not irrotational, then H is not constant over the entire region, but along any particular streamline, H will have the same value. Along another streamline, also H will be a constant. The two constants need not necessarily be the same. Whereas if you consider an irrotational flow, then the H is the constant at all points in the flow. Right? So here, H can be a constant along the streamline or along the vortex line, and then we may then give a meaning to Aris' statement that H equals a constant surface is covered by a network of streamlines and vortex lines. So I won't really go into that, but clearly we have proved here quite rigorously that in the case where the flow is not irrotational, then H will be a constant along the streamline alone or along the vortex line alone, not the same value in the entire region of flow. Are there any questions on this proof? Now we will move away from the perfect fluid. So there are many other possibilities you can consider and prove for various other cases, but we are not going to get into it. Clearly, the Bernoulli theorems all are governed by definition of a particular quantity called H, which contains a pressure curve, and this is referred to as a kinetic energy, and this is referred to as a potential energy. Often, the Bernoulli theorem is interpreted as a theorem on energy. It is not an energy balance, as we have seen. It's an incorrect view of the Bernoulli theorem. So, might be we give a meaning to this as some kind of a mechanical energy, right? So, but we have not introduced the energy balance at all. This follows from nothing more than the equation of motion. That is not the same. The equation of motion is the principle of balance of momentum, not of energy. Right? But it so happens that in some special cases, right, we can get a set of terms looking like or representing energy, which we will again get back to when we discuss the energy balance. But so far, without even touching upon the energy balance, we have derived the Bernoulli theorem. So it cannot be a theorem representing a conservation of energy. Rather, it's a consequence of the equation of motion. Consequence of the momentum balance, which has the appearance of an energy equation. Now, let us look at what will happen for the more practically important case from our point of view, which we have been covering for so long, namely the question of incompressible. Now, we are simplifying incompressible, linearly viscous fluid. What will the Bernoulli theorem look like? Right? We looked at two forms of the Bernoulli theorem where H will be a constant. Right? So, what about the same situation for a perfect fluid we have seen? Now, what is the same? Take the case of incompressible fluid. Right? So, for which now, what is the equation for an incompressible linearly viscous fluid? Here, since we are considering incompressible, we can also invoke the special form of the continuity equation, which is holds whether the flow is steady or not. Right? And then the equation of motion, which we have seen for a linearly viscous fluid with constant viscosity, is given by 2 times is equal to minus rho times B. Right? So minus the gradient gradient of the pressure plus the viscous term, which we call the viscosity times the Laplace of the velocity vector c. Now again dividing by rho, right? I get this now expressed, last term expressed in terms of kinematic viscosity. Now again I can combine, so this is, again I assume the same. So the development is very similar. Here we are going to use the identity for v dot and then the gradient of the velocity, get the v squared term, right? So what would that lead to? We have already seen that. Half v squared, so this is identical, plus the vorticity, which is nothing but the curl of the velocity. Right? So we are going to use the same. So then I get, so what I will get is dv by dt plus w cos v is equal to, so that term is recovered for the incompressible fluid. So this is coming only from the acceleration curve. And we use that again to get to, here of course we don't have to worry about all those integral which I haven't explained quite clearly. But clearly here, because the rho is a constant, I can take it into the gradient. Right? Even though it appears outside the gradient here. The constant can be taken inside the derivative. This is actually simple. And then I have this extra term. This is nothing but so we see that we recover the equation for the perfect fluid with the additional, the two distinctions, one because I am considering only an incompressible fluid, otherwise I would have still this kind of a term, right? So I am considering only incompressible fluid, so that term has simplified, and not surprisingly I am getting an additional term due to the viscosity. So when we put, for instance, if I put the kinematic viscosity equal to 0, I will actually get the corresponding equation for an incompressible perfect fluid, which also we can consider. We haven't considered, right? Certainly a perfect fluid can also be approximated as incompressible in certain situations, maybe. But so that is what I get. So if I put the viscosity here equal to 0, what I will get is really the equation for the perfect fluid, which is incompressible. Now I get this additional term. So again I can consider steady flow. That is what most of the Bernoulli tables also said. Consider certain aspects of Bernoulli table for unsteady flow, so we won't get into it. So steady flow, then the equation is we can write this as now the gradient of h equal to, which we have here as v cross w. Right? Because the w cross v is going to come over this side, it can be written as plus. So what you can now compare is that for steady flow, except for the fact that the h here is slightly different, because we are considering in general a compressible fluid. The equation is identical to what I have there, except for this. Right? Now, if I want to, so here, suppose even if I consider the irrotational flow, I am having this. It's a bit difficult to interpret directly, so I am going to use another vector identity which is given in Aris, and that is for any vector A, I have the curl of the vector A is equal to the gradient of the divergence of the vector minus the Laplacian of the vector. This is, I don't remember the reference, but it is one of the, if you go to Aris, chapter 3 or so, it is given a lot of vector identity. Probably we have covered it in one of the assignments. I don't remember. Right? But if I now replace this, clarify any vector A, B is also a vector. So I get this. Right? So now applying it in this particular case for an incompressible fluid, this is 0. So that is a 0. So for applying this equation to the incompressible fluid, right, and the velocity vector, I get that the Laplacian is actually given by minus the curl of the vorticity vector. This is somewhat striking result. So now, I can sort of rewrite this. So I write this as, so that I'm getting a minus, so I'll rewrite it as minus the gradient of h is equal to W cross B. We write it like this. Plus, that is a steady flow of an incompressible linearly viscous fluid. Now clearly, if I consider further an irrotational flow, clearly h equal to a constant in the entire flow region. Because W is identically 0 for irrotational flow, and so the gradient of h is 0. So again, I recover this very strong result. So for the irrotational flow of an incompressible linearly viscous fluid, steady irrotational flow, again I get that h is a constant in the entire region. The irrotational, right, steady, and incompressible. All those conditions. Whereas here I don't have to impose a condition that it is incompressible. No, is like left it. Yeah, that is good. That's good. That's important. We have to keep that. So that is what I have. And what if the flow is not irrotational? Here we show that if the flow is not irrotational, I can write the corresponding equation here. The minus of the gradient of h. So we were able to show that the h must be constant around streamlines or vortex lines. Here such a simple interpretation will not possible. If the flow is not irrotational, then I have to deal with this. I have to deal with the fact, just as there I have to deal with the fact that the gradient of h is W cross B minus. I have to deal with now the additional terms. So we cannot get that h will be constant around streamlines or vortex lines. But what theorem comments is that h then can be shown to be a constant along vector lines of the vector, very complicated vector, since it doesn't seem to have any obvious physical significance. So what theorem means by a vector line is a line, any line, the tangent to which is a particular vector. So when I say a vector line, when a streamline is a vector line, vortex line is a vector line. The streamline, the vector is the velocity vector v, that would be tangent to the streamline at any point. Vortex line is also a vector line. The tangent to the vortex line would be given by the vorticity vector. So if I now form a vector, let us say A, which is equal to the cross product of W cross B and the curl of W, say that along that particular vector line, h would be a constant for linearly viscous fluid. This is purely of academic interest because I don't know if this kind of a vector line really has any striking physical significance. So we will just leave it at that. But you should try to take the arguments that we gave for the perfect fluid, right, to show that it is constant along the streamline as well as constant along the vortex line, to see how such an argument would lead to. I haven't verified it, right? So because I find it particularly interesting. But in fact, you should follow those arguments for this new case where the gradient of h is effectively given by this, and then show that if I form a vector, that is a vector line corresponding to this means These are lines or curves in space for which the vector A would be a tangent. That's what he means by that. Vector line for the vector A given by this. If you consider, just as we consider streamlines and vortex lines, we can consider another set of curves for which this vector A, which is given by this complicated relation, would be a tangent at every point. Then, along that vector line, he says this relation implies that h would be a constant. So I will leave it for you to trace out those arguments and prove for yourself. Right? So I am not going to go into it in greater detail. Are there any questions? So this completes our brief discussion of the Bernoulli theorem. The important thing is that there is a quantity called h that appears in all the Bernoulli theorems, and they all deal with h being constant under some conditions, and h being not necessarily constant in the entire flow region. We have seen 3 cases where h can be constant along a streamline or a vortex line or some other special vector line, not necessarily for irrotational flow. The theorem says that h is a constant in the entire flow region. So unless we know the flow is irrotational, we cannot really comment anything on h. Yes.
W cross V is a plate tangent to H.
No, that's what I don't want to get into that argument now, because I have 10 minutes and I want to use the time now. It will take probably more than 10 minutes if I try to prove that without having first thought about it. Right? So I will admit that. Right? Something looks so clear here because I have thought about it at least 10 times. So I am not that smart. But I just spend so much time to make sure that I look smart in front of you. If at all. Right? So I haven't spent so much time on that. I don't want to get it, and I am not smart. I don't want to get involved in trying to explain that. Since we have touched upon the quantity irrotational flow, I want to briefly discuss about the consequences of irrotational flow. So, irrotational flow means simply that this is basically irrotational flow. So, there's another question we said to be, I'll probably get into that shortly and also leave that for you to argue with. Right? Irrotational flow. We have already seen that the curve of the gradient of some scalar, let us say, some scalar phi, you not necessarily be the phi associated with the body, any scalar phi, right? Take the gradient and then take the curve, then I get a vector, then I can take the curve of that vector. So that vector we have shown is 0 vector. That can be proved very easily. It's there in the assignment 1. Now you can also show that suppose the curve of a vector is 0. Suppose, looking at the converse, if that vector is the gradient of the scalar, then to show that the curve of that vector is 0, that's one thing that is very easy to show. But it can also be shown that if the curve of the vector is 0, then there exists a scalar for which the vector is given by, let's say, minus or plus, it doesn't matter. This is 0. So if this, then this is true. So what this means here is that irrotational flow, since the curve of the V is, I am not going to get into the proof of that, but it can be shown. Right? So this theory means that the velocity, you have to be careful about the sign that I want to follow, because some books use minus the gradient of potential. So clearly by using this theorem, if the curve of a vector is 0, then that vector can be expressed as a gradient of a scalar. I will now argue that the velocity field itself can be expressed as the gradient of a potential, which I know denoting by the big letter phi, right? And for this reason, irrotational flow is also referred to as potential flow. That refers to the fact the velocity is given by the negative or the gradient of a potential basically. The negative sign is just a sign dimension. So what this means immediately in Cartesian coordinates is that dx is minus d phi by dx and so on. For v1, v2 and v3, right? So this is what it means. Being given in terms of the potential. Now this will give us two functions. One function is a stream function, another function is a potential function. There are differences and similarities between the two. We have seen that certain special cases called the planar flow, which we have given examples in the Cartesian and spherical polar coordinates. Right? The velocity can be expressed not as a gradient, but as terms of the derivatives of the stream function. Here we are seeing that the velocity can be expressed as the gradient of a potential function. Important to remember that this is not restricted to two-dimensional or planar flow. This is valid for the entire three-dimensional flow. So while phi flows as well, sine is valid only for planar flow. That's useful or can be defined for, because we saw that the important criterion for defining psi is that only two of the terms in the continuity equation are non-zero and the psi is defined, the velocities are defined as derivatives of psi, so as to satisfy the continuity equation. So the stream function is somewhat limited in that sense. But the restriction here is this is applicable only for irrotational flow, but the stream function can also be applied for irrotational flow, but only for planar irrotational flow. Right? The stream phi is valid for irrotational flow. That is a restriction. Even though it can be applied for three-dimensional irrotational flow also, whereas the psi is valid only for planar flow, that is its limitation. Right? But not restricted to irrotation. So when the potential function not restricted to planar flow, we can say it like this, but restricted to irrotational flow, the stream function cannot really be extended to three-dimensional flows, but it can be applied for all planar rotational flows. The restriction irrotational, doesn't apply. Can be applied for rotational flows as well. Right? So these are the distinctions. Now we have defined a streamline. You should go and verify that if I for instance have a two-dimensional planar flow given in Cartesian coordinates like this, such a function. This is now a line because we talk only about two-dimensional flows. In Cartesian coordinates, if I express the stream function like this, then you have to prove that this is a streamline actually. It's quite easy to prove. Again, stems from the fact that the normal to the curve is given by the gradient of psi. Right? And if you go back to the definition of psi in terms of the velocity, you will immediately find that the velocity vector will actually be tangential to the curve. Actually be orthogonal to the gradient of psi. So you can prove that the streamlines have an additional significance, the stream function rather has an additional significance. Psi equal to constant, right? The Cartesian coordinates will give me the equation of the streamline, right? That represents a streamline, which means if I plot psi equal to c, right? By varying the constant, I get various streamlines. The velocity will all be tangential to the psi equal to constant curve. But now we focus on potential flow. The important equation that comes when I talk about the incompressible fluid is that for now, since the incompressible fluid, the divergence of the velocity is zero. Now I am talking about irrotational flow of an incompressible fluid. For the irrotational flow of an incompressible fluid is equal to 0, and which implies that this is the governing equation for the irrotational flow of an. So because it is expressed in terms of the Laplacian, the advantage of this equation, as suppose for instance for the planar flow involving the stream function, we saw that the Cartesian coordinate for steady creeping flow, the equation to be satisfied by the stream function is the Laplacian square of the gradient power 4 operator acting on site. It's a scaling operator, it's a Laplacian twice rather, right? The 0, we saw that when we go to, it cannot be extended to spherical polar coordinates because that will, the stream function is not really defined in terms of the gradient directly, right? So for that we saw that the corresponding equation was actually e power 4 psi is 0. However, because we have seen the Laplacian can be easily extended to spherical polar coordinate by any curvilinear coordinate, this equation can be directly applied to any curvilinear coordinate system, and that's the advantage of this one. The main restriction is that this equation is valid only for irrotational flow. So let me take an example. Just define this system. It's a very standard problem. Now, if you consider that the planar flow is spherical polar coordinate or a sphere, irrotational flow, I will consider a cylinder past fluid flowing past a cylinder. And I now consider it is irrotation. So the cylinder is cross section is given by this, and I will denote this as the x vector, the x axis, y axis is the plane, and then the velocity, free stream or the far from the cylinder velocity is given by v infinity times ex. That means far from the effect of the cylinder, velocity is flowing uniformly in the x direction alone. That's in that case. Now, the equation, what I am going to consider here is the equation only in two-dimensional case. Even though we are not restricted to two-dimensional case, we can assume that the cylinder is sufficiently long that the third dimension z, its effect can be neglected. And we will now consider the special case where V is equal to ERC plus E phi, and both ERC are dependent only on. This is somewhat like, it's actually then what the interesting thing about this is that this can also be treated using the stream function approach, and that's what one of the assignments asks you to do. So what is the advantage now? We can go to the equation of motion and solve for the velocity profile, but what we will do rather, we will solve this phi just as we solved for the stream function in the earlier case in the planar flow. We can directly solve this very simple equation to solve, especially in two dimensions. You get another linear equation, and then we would have to convert the boundary conditions to boundary conditions on phi, get phi, and then we can get the velocity. For instance, velocity is given in terms of the Laplacian is B is simply given by minus. So I can now get ERC and B phi once I have found phi. So rather than solving for the velocities directly, I solve for the potential function because of the irrotational flow, right? And then I construct the velocity from the potential. Are there any questions? So we continue this problem on Monday.